All right, so I just wanted to kind of review a little of what we've already discussed and learned. So this shouldn't take too long. And then tomorrow my plan is to have you do a quiz. We'll do a quick review first on just how to find EV sum, SE sum, and then use that to find the chance of something happening. So we'll review that first, and then I will have a quiz on that stuff tomorrow. Okay, but we will review before, and of course it's open notes. Okay. All right. So in chapter 3, which was a long time ago, back in September. Okay, we learned, but we did make these recently with the surveys that we did last month, okay? But in chapter 3, we learned about density histograms, or they're also called empirical histograms. I think this should be in your blank, right? Histograms we saw in chapter 3 are called empirical histograms. That's your first blank in your notes. And that's because they represent data, or data, however you pronounce it. So with the random survey that you did last month with the heights of students at SJH, that was an empirical histogram because you took this data and you graphed it, right? You used the percentage, right? Our blocks represent percent, okay? The area above a class interval, I just said that, sorry, represents the percentage of data values falling into that class interval, right? So if we're talking about income of families in the US, we know this rectangle right here represents the percentage that are between this and this, right? And then when you made your posters, you also did each rectangle or interval represents percent within that height, right? Okay, well now probability histograms, they represent chance. All right, so those that we drew represent just data. We have this data, graph it. Probability histograms represent the chance of something happening. And then the area above the interval represents the chance for that specific interval. Represents what? Tell them, guys. Okay, so for example, we have this probability histogram when you roll 2 dice and you add what you roll. You add the 2 spots on the die, okay? This would be a probability histogram because what's the most common thing to roll? A sum of 7. That's the most common, right? That's the most likely thing to happen. What's the least likely thing to happen? Getting a sum of 2 or getting a sum of 12, right? Because that would be a 1 and a 1 and a 6 and a 6. So this represents the chance of getting a sum of each of these. Does that make sense? So it's not a normal histogram like we've been learning and we see a lot. It's a probability histogram, so it shows the probability. Come on, why isn't my thing? Thanks. Thanks for noticing. Okay, so we can get a probability histogram for a chance process by finding the chances of that and doing a histogram, right? An empirical histogram, I don't know, is this in your notes? Yeah? Okay. We can get an empirical histogram for a chance process by repeating it many times and then doing a histogram. And then the more repetitions we do, the closer the empirical histogram, which is our actual data, will represent the probability histogram. And that's the law of averages. What? Oh, yeah. Probably none. But But yeah. Hopefully Nate is watching, but or will watch, but and Shay and Cairo. Yep. Okay. Okay. Um. So go back to this example with the rolling 2 die. Oh, of course, my clicker's not working. Go back here. Okay, so let's say we actually did this. Okay, we did an experiment. Each of us rolled 2 die 10 times. We added up, blah blah blah, right? And if we were to graph what we actually got, the more times we repeat this, the closer it should match this, right? Just like when we tossed the coin and we measured how many heads we got and tails, well, mostly heads out of the total. Okay, that was the law of averages, which says the more times we repeat something, the closer it should be to what we expect, right? So this is what we expect when we roll 2 die, but it may not look like this. Like if we only rolled it 20 times, would it look like this? Maybe, no, it might be totally whack, right? Maybe we rolled 2 a lot more times than a 5. But then the more times we repeat it, the more it should look like this. Okay. So this just shows an example. Okay. So if we did it 100 repetitions, it might look like this. Okay. That might be one example of 100 times. 1,000 might look like this. 10,000 might look like this, and then the probability. So do you see, as we increase the number, it gets closer and closer to what we expect, right? Which I think is just common sense, but it does have a name, which is the law of averages, okay? Let's see what else. Okay, and then the probability histogram for the sum of the draws will approximately follow the normal curve. If the number of draws, which this is what we talked about yesterday, okay? So this is just a review from yesterday. If the number of draws is large enough, even if, like we talked, or I mentioned yesterday, even if the tickets in the box don't follow a normal curve, it doesn't matter. It matters how many draws we take from that box. So as long as we get a large amount of draws, then the sum of the draws will follow a normal curve, okay? Which is why we can use that menu 652 shortcut to find a chance of stuff happening. Are we good here? Okay, this just reviews EV sum, SE sum. I don't think we need to review that right now. Well, just say not right now. Yes, we do. Okay, so basically what these examples show us. Okay, look, if we had a box that had 1 0 and 1 1, that's split like evenly, right? 1 0 1 1. So the histogram of that would be uniform because they're the exact same. But if you look at 100 tosses, 400 tosses, anyway, if you look at that, the empirical histogram, this approaches the probability histogram. Now let's look at a box that's like this. This is a histogram for the box. Is it normal in any way, shape, or form? No, right? We have 90% are zeros, 10% are ones, or 9 zeros and 1 1. Okay, but even if we take the sum of the draws here, 25 draws still follows a normal curve. Isn't that crazy? So even if you took The sum of the draws, 100 draws, it just looks more normal. 400 draws. Okay, so even if the histogram of the box is not normal, the sum of the draws will be. Now, and oh, here's another one. Say we had 1, 1, 1, 2, and a 9. So that's the histogram of the box, but the sum of the draws still follows the normal curve. Crazy. But that's why the normal curve is magical. But not everything's normal though. So sums, I think this is part of your notes. Sums, averages, percentages are normal, but products are not. So when you actually multiply things, you can't do the product of the draws and not be normal. So it has to be sum, average, and percent. I just turned off my camera. Sorry, it was in the way and I was annoyed. Okay, so sums, averages, percentages are normal, products are not. So that's why eventually, well, pretty soon in the near future, we are going to not just talk about EV sum, but we're going to talk about EV average and EV percent, because all three of those are normal or follow a normal curve. But that's why we're never going to learn about EV product, because that doesn't follow a normal curve, okay? All right. And that is it, folks. So